So, hello, my name is Jan Carstensen. I'm from the Real-Time Systems group at the Leibniz University in Hanover. And today I would like to present Real-Time ROS, a real-time extension to the robot operating system in its version 1.x, while our project started prior ROS 2 being announced. Just a short and very brief motivation. Why do we want to do real-time? Well, a lot of robots work quite well without. Some, especially if they get bigger in size or more complex or are operated in, well, unsecure or high-risk environments, they need to, deliver some sort of real-time guarantees and performance. And that's what we would like to do with ROS. So why do we choose ROS and not one of the other open source real-time frameworks? We believe that ROS offers quite a unique usability and a lot of tools, and well, we have a lot of people who use ROS and who would like to stay close to ROS and not learn to work with a complete different ecosystem and framework. I would like to give you a short introduction, show you a rough architecture of what we've been building and using, describe how we managed to use publish, subscribe, and service communication, show a little bit about what we've been doing in real-time debugging, show some example code, and talk about some current work which is actually ongoing at the moment. First of all, what was the design goals for us? As mentioned before, usability was a hard topic for us. We wanted to have a software which is really usable and which not take that much extra configuration and possibly hide a lot of the extra work done or necessary for real time. One of the most important goal for us is we wanted to at least suffice or be able to deliver real-time performance, at best, hard real-time performance. Safety is an issue as well, especially when using hard real-time systems, which are often deployed in high-risk or critical scenarios. You need to deliver some level of safety, the more the better. Still, this led us to start to focus on a small core and only take parts of ROS which we try to port to real-time and get up and working. So what did we do? We discussed forking the entire ROS stack and just trying to port it to ROS, but since this is definitely too big, we started to take out parts. These parts being publish, subscribe, communication, services, and the other essential parts to be able to create a small system of real-time ROS nodes on one PC as well. So network has not been included yet. We wanted to have ROS beside this, so we wanted to still make use of all the ROS tools and all the ecosystem and use as much from ROS as possible, not only the API. So our real-time ROS nodes, especially during initialization, are using the ROS parameter server and all the other stuff we've all been are using and are accustomed with. For real-time ROS, we're using ACH, a shared memory library which is open source and allows for real-time communication. And our main development has been focused on Xenomai in its version 2.6, but I'll come to that later. When talking about real-time, usually you want to have two things. You have always a time-triggered behavior, so it's always you look at cycles and at latencies and its jitter. And so I would like to just show you this for a little moment. Especially when comparing different real-time operating systems which are necessary, like for instance Xenomai, since Ubuntu and the mainline Linux kernel does not offer real-time performance out of the box. It is necessary to patch the kernel and sometimes add some user libraries. Xenomai does this, PreemptRT is another example. All are mainly compared by cyclic tests, meaning you have a cycle, you say like, okay, I want to have a node or a program running at a few hertz, maybe some kilohertz, and you measure the difference between the scheduled time your thread should wake up again and the actual time it did. And this is basically the system latency which is introduced, and this is something, even though you build on top of it, you cannot get better than the system latency. This is introduced in every step. So on the right side you can see a plot. This is basically a histogram. On the vertical axis you can see the occurrences in a logarithmic scale. On the horizontal axis, the user space latency. In this case, ROS is running in user space, therefore this is what we're looking at in microseconds. What you can see is that the vast majority of all occurrences is below 5 microseconds, which is nice, which is very nice. But the more important part is that it is bounded. So even though many test runs have been performed, 22 microseconds is the maximum latency expected or shown in this case. So this is the actual behavior we want to see. And we do not want to see this only as a system latency, but for ROS as well. And this is why we started with benchmarks. The first benchmark is the rate benchmark. ROS nodes are mostly controlled or time controlled by rates. You can set a loop rate and control how fast your thread shall run again, or use the spin behavior where basically ROS does this for you. So we just took a system, and on the system we performed just a benchmark in ROS. We put in a loop rate, and we measured the difference between the actual time we would have liked the node to run and the time it actually ran. Because in real-time systems we're talking about worst-case scenarios, so all these tests have been performed on a stressed system. So we introduce a bunch of load for the CPU, we do a lot of extensive computation, we copy in memory and we copy from disk to disk, and do as much as possible to come very close to a stressed system and get a worst-case scenario. In this scenario, again, the axes are the same for all diagrams, and we had 2.7 milliseconds average latency, and 21 milliseconds max latency, which is okay, but as you can see, the plot looks a little bit more jittery, and this is not the type of behavior we would really like. So our goal was to try to improve this. For real-time ROS, we were able to get measurement reading, as you can see here. In an average, we had 0.6 microseconds of latency, and below 15 microseconds in max latency. On the system we performed this, we had around 100 microseconds of system latency. So this is basically what we would expect to see. And are therefore quite happy with the results. Besides being able to control a thread to run under real-time constraints, using publish and subscribe is one of the main ways to communicate. And without these, our approach would not differ from the possibility to just install a real-time operating system and just run a thread and use real-time tools to interface with ROS. So publish-subscribe communication is one of the key aspects. We try to keep the API as close to ROS as possible. So the publish and the callback is very close to the ROS API. Very close means there are some exceptions we need to make, especially because all our memory, all our variables need to be pre-allocated. Therefore, we need a maximum message size. ROS allows us to just publish a lot of things, which is nice, which gives us a great flexibility. But in a real-time system, we need to know prior how big the maximum message will be. And this is one of the parameters added at this point. As you can see, after publishing, the message gets serialized and transmitted through a shared memory, and the other node then uses a poll, which is, very similar to ROS 1 behavior. After the deserialization, the callback is called and executed. For services, we basically used ACH as well to communicate, since we have already implemented it for publish and subscribe. We only had to change a few things. In ROS 1, most of the services are loosely coupled, so as soon as you call a service, it first asks if the service is already there, if it's available. That's why we always use wait for servers and things like that. This is something we do not want to do in a real-time behavior. Therefore, for real-time ROS, all services need to be initialized before running the main loop and starting the real-time behavior, and therefore we have a permanent coupling. So the server and the clients are permanently coupled, and the connection is always active. For publish and subscribe, again, we performed some benchmarks. Again, we started for ROS 1X. We're using Indigo. Sorry, I did not mention that before. We're using Indigo. Again, a stressed system. And we came up with 210 microseconds average latency and 27 milliseconds in max latency. The latency here was measured that we took a timestamp on the system right before sending the message and directly when the callback came back to compare what time it took for the message to go. We took basically the time message. So we sent the timestamp over to the subscriber node. So it's a relatively small message in this case. For real-time ROS, we were able to receive an output, as you can see here. We had an average latency for around about 45 microseconds and a maximum of 180 microseconds. Again, this is basically what we would expect since the polling behavior runs at roughly 10 kilohertz and asks if there are new messages. So we will have relatively constant behavior between 0 and 100 microseconds. So again, we were very happy with the results and moved on to test service. Oh, sorry, we did not move on yet. We again counted the messages, and especially on a stressed system, we found out that ROS was not able to deliver all messages, even though on one system. I was personally surprised that there were no really high-level warnings or errors going on. I was expecting something like that in this case. But still, I mean, it's well above 99% of messages being delivered. So in most cases, it will not be a problem, but especially when you come to real time, it's not only important that when an answer comes, this is beyond, inside of the deadline, the answer needs to come. And this is very important. For services, again, we performed benchmarks. For us, you can see the time takes a lot longer than publish subscribe. This is due to the fact that the connection needs to be established priorly, and we were around 26 milliseconds of average latency and around 50 milliseconds in a maximum case. For real-time ROS, the performance is very, very near to what we expected or what we saw with publish subscribe. Since we are aware that an answer or a request should come in the next time, we do not have to poll, we can just wait for the answer to come and therefore basically eliminate the maximum of 100 microseconds introduced through the polling behavior. In both cases, all messages or all requests came there. This test was performed by taking a timestamp right before calling the service and directly after the service returned. I would like to talk a little bit about real-time debugging, because my experience with real-time is it's nice when it's working, but the biggest problem is to get it there and to find out what's going on. So we ported the ROS console to be real-time safe, so we were able to do some real-time safe debugging. One of the biggest problems is if you use a real-time safe version of print, which basically means the print is not executed directly but taken to another thread, then your logging is not actually there where you would expect your program to be. So when your program crashes, it could be that it's crashed like a few hundred lines of code below the point where you would see your output to be. This is basically why we added a few real-time related signal handlers which try to figure out when something went wrong and print a stack trace, so you're really able to find out at what point this went wrong. And this is usually, and can be configured, printed to the console as well. To show some example code, how does it look? This is basically a ROS talker node, which just includes the ROS header, the standard message time header, initializes the node, and after initializing, this one pre-allocates the message data as well to be better compilable. Sorry. And in the main loop then just takes a timestamp and sends it. This one runs with 1000 hertz as well. The real-time ROS node basically just switched the header, so we need to include the real-time ROS header instead, and we switched the namespace. This is basically done because we would like the option for hybrid nodes to be either in real-time or non-real-time. We wanted to be able to use a lot of the ROS functionality during initialization or debugging phases where we're not in hard real-time. Therefore, a namespace change has been included so that we can have hybrid systems, or just by trying out real-time ROS, you do not break your existing ROS system, so you can just try it out besides. Otherwise, ROS or the RTROS uses the same message definition, so you can include and use all the messages you currently have. And yeah, well, we believe therefore the usability and the compatibility is quite high, so it's easy to port an application or to use this approach to develop new ones according to the standard ROS documentation it schemes. So I would like to talk a little bit about the current work. Of course, we are working on testing and improving the current state of work. We started to set up a continuous integration testing system where we want to be able to test for real-time constraints as well. Therefore, we cannot use as much virtualization as we would like to use, but we use dedicated systems with real-time operating system installed and just trigger the jobs there. Currently, we are testing for Xenomai 3.0, Xenomai 2.64, and Preemptor T. I'm not entirely sure which version. This is possible to be extended in the future. All our work or all our design on Xenomai, except the signal handling and mode switch tracking and some special stuff, is based on the POSIX API, so it should be exchangeable to most real-time operating systems, and well, you could run it on a default Ubuntu as well without, well, real-time guarantees, but just to debug it, test it, this is doable. Besides testing and improving, currently there is an external evaluation going on, so a group outside of our research group is evaluating this, and afterwards this is finished, we are planning to completely open source everything we've been doing so far. I'm very positive to do this in the next few months, so I'm hoping to be able to release this this year, of course. And we're working on basically 2 new features. The current state of real-time ROS has been focused on single computers being able to span a real-time system over a few nodes, but still on one system. Network communication and time synchronization are currently ongoing topics, which we are hoping to be able to include over the next, well, months, years, as soon as possible. So, to show you a little overview, what is currently possible to do, you can use publish and subscribe. Well, not all publish and subscribe options, but I believe the main ones. Services are possible. You have access to ROS time, rate, and all functions needed to control your node. We ported the transform library, which works quite well, and you have access to the console. So you're able to set up, well, a small system, not distributed, but based on a single system, with real-time ROS and ROS nodes alike, and communicate. Since both use the same message definitions, it's not able to communicate directly, but you can just relay the message very, very easily. What are the problems? Well, one big problem are drivers. We are usually using a lot of hardware, and we need all parts of our working system to be real-time compatible. And a lot of drivers are not, and they're a closed source, so porting them is hard. For instance, graphics drivers tend to introduce a quite big amount of latency. Besides drivers, the real-time restrictions. While this middleware, the interface and the framework allows you to perform real-time operations to some degree, the user code can definitely break it. So there are a lot of things you're not allowed to do. For instance, you need to pre-allocate all your memory you're using, and you need to refrain from using any unbounded methods for possibly optimization or something like that. And sensors. Well, while most of the robotic systems use a few sensors, it's nice for them to be in real time as well. Otherwise, the reaction to a sensor input would not be real-time safe. And currently, well, a lot of sensors use USB, which is not very nice for real-time performance. So the availability of real-time safe sensors, which are affordable, I must say, is limited. So, thank you for your time, and I believe we have like 1 minute for questions. Yeah, sure. Go ahead.
Yep. Do you expose thread priority in the RTROS interface, or is it?
Yeah.
So thread priority is like associated with publishers and subscribers, or is it the native like POSIX thread priority? Yeah.
Basically, for Xenomai, there is an extended priority model which is exposed entirely. You can use it. It's on node basis, so not for publisher and subscribers. We do not prioritize the communication, only the nodes currently.
Hi, thank you for the presentation, really interesting. I was wondering about three things. First, if you use shared memory, why do you still serialize all your messages? Because you could just exchange pointers essentially, like nodelets for instance do, or RTROS can do if you share your note or you put your notes in one process. Two, can you say something about how much you had to change to get your timers so accurate? Is it just due to the fact that you use the POSIX library from Xenomai to get your timers real-time safe? And the third one, I'll just wait because otherwise you won't remember.
Okay, I'll start with the first one, maybe rephrase or repeat the second one. The first one, basically we used ACH, and especially for strings and when you transmit arrays, it's better to serialize them, and the option was easier. And the latency introduced during serialization is at this point so low, and we're not optimizing to this fine level yet that this has not been an issue yet. This is definitely an idea to try to reduce the amount of serializing, deserializing, but has not been a focus yet. Could you rephrase the second question, because I did not really get that?
So you showed that latency plot of the worst case execution time basically for your timers, the ROS rate benchmark that you did, and I was just wondering how much you had to change in the actual implementation to get down to that level of execution time, other than just changing things to the Xenomai POSIX library.
Very, very little actually. For the rate, it was very, very straightforward. Most of the problems arose with debugging and trying to add functionality to be able to do things and to find out what's going on and what's going on wrong.
Okay, well, and the third one was, why did you not use TLSF, for instance?
Sorry, what again?
Well, you're using, you said that you had to pre-allocate everything, which is true because you can't do any dynamic memory allocation. But if you use a real-time safe dynamic memory allocation infrastructure, basically, you could avoid that. So I'm wondering why you did not go that route.
Has not been a focus yet. We're definitely going to look into this in the future, but currently we're working with pre-allocation.